Okay, we're going to start this example where a plane lands on a runway with a velocity of 100 meters per second to the right. So we're going to call our initial velocity 100 meters per second, and this will be positive. It slows down at a rate of -5 meters per second squared. Now, they're not always going to just tell you that it's -5. They're going to assume that you know that if you have a positive velocity initially and you're slowing down, that your acceleration is negative. So kind of review back the few slides ago, or the first kinematics. And then it's going to come to rest. And the question is, can this plane stop on a runway that is 0.8 kilometers long? So really what we're looking for is x. And then we can compare that with the 800 meters. Okay, so you want to take a look at the 4 different kinematics that you have and decide which kinematic that you want to use. And most of them, the first 3 actually have time. The last one is the only one that doesn't have a time component to it. And we have our v sub naught, we have our v sub f, we have our acceleration, and we're looking for x. So this would be the kinematic that I would choose because the other 3 have time associated with that. I would also say that sometimes what is required, but not in this class necessarily, but in some classes, especially at the college level, is for you to solve it in terms of the variable you're looking for. Now, you don't have to do it that way for this class. You could just start putting numbers in. For instance, you could put in 0 there, 100 there, -5 there, and solve for x. That's perfectly fine. In fact, I like to do it that way. But I'm going to go ahead and just do it the way that you might have to do it at some point. Okay, and what we find is we get 1,000 meters, and so this plane is not going to be able to land on a runway that is 800 meters long with that particular acceleration going at that speed and wanting to stop. That's not going to work for it. Okay, here's another one that we could do, and we're traveling at a velocity, the car is, of 78 kilometers per hour. Now, we want to make sure that we are always in meters and seconds. So I need to change this. So don't forget your dimensional analysis. And we're going to go ahead and convert that by going 78 times 1,000 divided by 3,600. So 21.7 meters per second. And some animal runs in front of it. We basically have 100 meters to work with. And the question is, well, what acceleration is going to be required so that the car can stop in time, and how much time will it take for the car to stop? So a couple of different questions that you need to ask. So there are a couple things that you could use. You don't have time again, so you do want to stop. So probably again the 4th kinematic is going to be what you want to use. So we're going to go back, and the 4th one is used quite a lot, especially if you don't have time. That's a good one to use. And so now we can go back, and we know that the final, and I'm going to go plug it in just the way that I kind of like to plug it in rather than solve for your variable. Okay, so we're going to basically take 21.7, square it, subtract it over, divide by 2, divide by 100, and we get a negative 2.35 meters per second squared. And notice that makes sense because if you are slowing down to the right, which is, all indications from the problem is that you are going to the right. You have a positive initial velocity, you have a positive 100 meters, you must be going to the right or north or something positive. And so it makes sense that if you want to slow down, you're going to have a negative acceleration. Now, I've sort of run out of room on this slide, but you can calculate how much time it will take for the car to stop really using any of the first three kinematics. Like the first one, you could say x is equal to 1/2. So you have x is equal to 1/2 times v sub naught plus v sub f times time. And so you could solve for that time. So, but the second and the third one would work just as well. Okay. This problem is a little bit above and beyond what most of the problems are. I would say most of the problems are kind of just plug and chug. With this one, we actually are kind of asking what's going on in this whole process of stopping and decelerating and such. So what is going on here is that you again have an animal that is going to run out, okay, and you really don't want me to try to draw a deer, so it's going to look like a giant bug probably, but there's your deer, and it does look like a giant ant. But what's happening here is that you're kind of going along in the car, driving along, and this deer runs out. It's very big compared to the car as well. But what's going to happen is there's a reaction time. And this is going to be your reaction time. And the reaction time is that whole time before, you see the deer, you think, oh, I need to stop. Your brain tells your foot to get off the accelerator and put it down on the brake. And this is your total acceleration piece right here. So what you want to do is to solve for x right here. You want to solve for that acceleration from going your initial velocity of 32 meters per second and stopping with an acceleration of a negative 6.4. You want to go ahead and find your x. You want to find how much distance do you need once that brake has been compressed. How much distance do you need to stop? And so again, the fourth kinematic is going to lead you to an answer of 80 meters. So really then what you're saying is if you've got a total of 82 meters in front of you, you can let that car go for about 2 meters before you really need to compress the brake. That's your reaction time. So, if you're taking a sleeping pill or something like that, the reaction time tends to go down, which is never a good thing. So, what would your reaction time be? If you can travel, this car can travel 2 meters, which is not a very long distance. But if you can go 2 meters before your foot has to compress the brake, what we're going to say is, well, if we're going 32 meters per second, I'm just going to go 2 meters at 32 meters per second and go 2 divided by 32, 0.0625. And that's not a lot. It's supposed to be seconds. But, thankfully, for the most part, our brains work pretty fast. We're able to get that foot doing what we want to do pretty fast. So that's not a completely unreasonable reaction time as long as, you aren't taking a sleeping pill or something like that. So that is that problem. Now, I think this ends. Yes, the next video is going to be about falling objects. So we'll end there and we'll call this kinematics 2.